Hello guys, in this video we'll learn a few more smart pointer in Rust. As part of this video we'll cover RC, reference counter, cell, RefCell, OnceCell, LazyCell. These smart pointers along with many other in Rust are pretty useful if you know how and when to use them. And trust me, once you know how to operate with these smart pointers in Rust and when to use them, your code looks like a pro Rust developer. So make sure you stick around, watch till the end, understand, and if you have any questions, any queries, feel free to drop in the comments. Now, as part of this video, we'll take a bottoms-up approach. That's what I do in all of my conceptual videos. We'll try to first run into the problem that requires these smart pointers to solve. So let's first of all try to get into the problem so we can grasp when we really need to use all of these. So let's get into any of your favorite text editor. And by the way, as we start, there is a link to my Discord in description. Make sure to join it. We do tons of discussions there, and obviously we are building up a community there, so you can interact with lots of amazing people in the community. So make sure you join it. So move to your favorite IDE or text editor, and let's take a pretty straightforward and simple example. So let's say we have a struct node and derive debug, and we have data for this node, which is an i32, and then this node points to some other node which could be optional at times, so optional of let's say node. Now we might want to box this to efficiently utilize our memory, but again, box is another smart pointer which we'll cover in a separate video. For today we'll keep our focus only on RC cell, RefCell, OnceCell, LazyCell. Now let's say we have some nodes, so node 3, and that has a data of 10 and points to none. So let's say this node doesn't point to any other node, but then we have a node 2, and that has a data of 20, and that also points to some node 3. Similarly, let's say we have a node 1 that has a data of 30 and points to some node 3. And if we try to write this, now as you can see, as soon as we end up writing, we get this error here, and that says used of moved value. Now why it occurs? Because node 3 is already moved here, and in Rust, going by the principle of ownership and borrowing, we know that we cannot reuse something that's already moved. So what are your options? Could we solve this problem? Now, if you think it for a minute, you might, consider I can clone it, which is basically using clone here, and then we can just clone. And if we write, boom, it solves our problem. But does it really solve our problem? If we think for a minute, now node 1 is pointing to node 3. Fair enough. Good. That's exactly what we want. But node 2 is not pointing to node 3. It's pointing to a clone of node 3. So if you try to access node 3 from node 1, it would give you this node 3. But if you try from node 2, you won't be able to see this node 3 but a clone of this. So what happens once you modify something in node 3? You would be able to visualize those changes from node 1 but not from node 2, because node 2 is pointing to a clone of node 3. Again, this is pretty important to understand this thing, that node 2 is not pointing to node 3, it's pointing to a clone of node 3. So actually you have not solved the original problem, which is node 2 and node 1 wants to point to node 3. That problem still remains unsolved with this clone that we just did. So then how do we solve this problem? Now, because the problem that we have in hand is node 1 and node 2 should be able to point to node 3. And it's not as straightforward in Rust because of ownership principles, because only one could be the owner of one thing, one value. So if the ownership is moved, you cannot use it. Now, there comes the introduction of RC, reference counting, a smart pointer that helps you take the shared ownership. And how do we do that? Now, before we solve our problem and try to get into all of these smart pointers, RC, cell, RefCell, and everything, I would highly recommend you guys, if you still haven't understood the problem, please rewind and try to understand the problem before moving on to the solutions. So what we'll do here is, first of all, we'll wrap our node with RC, and then what we'll do is here we'll create the node using RC new, and now right here we would say RC clone and node, and similarly we do right here RC clone node 3. Okay, now as you can see, the errors are gone, and one might now think, hey, we are cloning here as well, but guys, RC clone is different from the clone that we saw when we tried to solve the problem with the clone. That clone creates a deep copy. This clone just shares the ownership and gives you the ownership of the data, which is here node 3. Now, how do we ensure that RC is actually sharing the ownership and not cloning or deep copying node 3? We can do that by checking the strong references for node 3, and that we can do using the strong count. So we can use dbg to check line by line. So RC strong count, and we want to check the strong count to node 3, and let's simply copy this and we just use it once here and once we try to put it here. So basically what we do here is we are checking the strong count of node 3, the references here, here, and here. Now let's try to run this. So cargo run quite. Okay, as you can see on 15.5 our reference count is 1, then the reference count is right here. Basically the reference count on line 22 becomes 2, and the reference count on line 27 becomes 3. So that's how basically we ensure that, hey, node 3 is having the references but not it's sharing the ownership and not so one owner is node 3, one owner is node 2, and one owner is node 1. So it's a shared ownership. It's not deep copy or cloning your. And we can we can just drop and also check the count as well. So let's say one way is we could just try to use it here, and right here we just drop and we drop our node 2. So we drop node 2 here, and let's write that, and we rerun. Okay, as you can see now, after basically line 21 and line 27, the reference count is same because it's 1 here, then it becomes 2, then it's dropped, so the reference count decreases, and again it becomes 2 when there's a new reference added. So basically, as you guys can see, we can share the ownership using a reference counter. It's as simple as that. When do you use it? When you want to share the ownership. Now let's move on to our second topic, which is cell. So let's say I want to modify here data of node 3 or node 2 or node 1. I need the mutable reference, otherwise I cannot modify. What cell helps you is it provides you mutability of those types which implement the copy trait even when you have the immutable reference. Again, let's say I want to modify this data. Now we know that I32 implements copy trait. So what we can do is we can just wrap it in a cell, and which is basically using cell. And now I can modify data of node 3 or node 2 or node 1 without having the mutable reference. Let's see how can we do that. So let's say we just do is node 1 dot data dot set, and that is only accessible, as you can see here, if you have like the value content in a cell. So right, as you can see here, we have in a cell. So what we'll do is, now instead of directly 10, we do it something like this: cell 10, similarly cell new 20, and similarly cell new 30. And we just try to set a new value. So instead of node 1 having 30, let's say I want to change it to 888, and we use dbg, and here we just spit out node 3. So what we could achieve is, if I try to modify, like because I have immutable reference, I cannot. But if I use cell, which is what we are doing in this example, as you can see, we are able to modify without any error. And now if I try to run this, okay, so as you can see right here, the data of node 1 is 888. It's not 30, it's 888, and the value of node remains as it is. Similarly, let's say because I'm using cell, I could modify the value of node 3 from node 1 as well. And how can we do that? Let's say if let some ref node, and here we just do is node 1 dot points, and what we can do is node, or we can do in dbg as well, node dot data dot set, and we set it to from 10 to, let's say, 1000. And let's just save this, and then we try to run this. Okay, so as you can see, now it says node 1 has its own value as 888, which is because we modify it here, and the value of node 3 becomes 1000 from 10,000, actually from 10, and that is also visible if we try to dbg our node 2 here instead, and we don't dbg, let's say, node 3. So let's rerun. Okay, so as you can see, node 2 has its own value as 20, but node 3's value is changed to 10,000, which is reflected in both. So let's try to see the both case as well. So this also ensures that using RC, basically we are pointing to the same reference and the ownership is shared. Node 2 is pointing to node 3 value 10,000. Node 1 is pointing to node 3 value 10,000. As simple as that. So this is where cell helps us, which is basically for all those types that implement copy trait, you can mutate the value without even having the mutable reference. So that's as simple as that. Let's discuss our third topic of the day, which is RefCell. Now, if you are able to successfully understand cell, then RefCell is kind of similar, but a bit different. So as I mentioned, that cell allows you interior mutability to all those types that implement copy trait. For example, data was here as I32, so we could, mutate it without having mutable reference as well. But let's say if there was string or vector, it was not possible because those types do not implement copy trait. So cell only allows you interior mutability when you have the implementation of copy trait. But let's say in case of our custom type or vector or strings, you don't have implementation for copy trait. So how can we mutate? So let's say here, if we want to mutate points, like let's say I want to change that node 3 points to, I would say, maybe node 1, and node 1 points to none. So how can we achieve that? Let's see what happens if we try to do as it is. So let's say if we try something like, let's say, node 1 dot borrow mute dot points to none. Okay, now as you can see, immediately we get an error saying cannot mutate immutable variable. Now that same is true if we try to mutate node 3 as well, meaning if we just have RC and we have our nodes which are immutable, we cannot achieve interior mutability. So then how do we solve this problem? That's where RefCell comes into play. Now you might think that, hey, isn't this against the the 101 principle of mutability and immutables in Rust? Like if you don't have a mutable reference, you cannot modify. But how are we allowing the modification here? That's because we are adding extra things like RefCell, which or cell. So basically RefCell and cell ensures that you can only change inside the object providing that property has cell. So let's say if I was not using cell here, I cannot mutate. If I'm not using RefCell here, I'm not able to mutate. So basically this is to provide the access to mutate inside but not the object to whoever is using. That's when RC RefCell comes into play. So now let's say, what if we try to use RefCell? Now let's try to use RefCell here to achieve interior mutability. So we just wrap our node in our RefCell, and then in our node 1, node 2, and node 3, all nodes will just wrap in RefCell. And same we do right here for node 2. And same we do for node 1. So all nodes look exactly the same, right? The same type. So we have node 1, node 2, and node 3. Now let's say we want to first of all go like node 1 dot borrow mute and dot points to none, let's say. And as you can see, this time we don't get any error. We don't get any error here because we don't have still node 1 as mutable, but we are still able to get a borrow mutable and basically set it to none. And similarly we say node 3 dot borrow mutable and points to sum of RC clone and node 1. So we share the ownership of node 1. We don't need this to import, we get it from RefCell directly. So now let's do a before and after. So print, we say before node 1, and here we'll just do is node 1 dot borrow, and similarly print we just say before node 2, node 3 actually, we don't touch node 2, and node 3 dot borrow just as I like set node 1 to none and then set node 3. This I have done because if we would have not done this, then RC and RefCell, these things can actually lead to memory leaks as well. So because node 1 will always point to node 3, node 3 will always point to node 1. So basically your reference count will never reach 0. And in that case, you are always leaking your memory. So let's copy this and we just say after and after. Okay, so we save it and all looks good. Now let's go ahead and we try to run this and check. So cargo run and quite. Okay, as you see, first node 1 points to our node 3 and node 3 is none, points to none. Then node 1 points to none and node 3 points to our node 1. So basically we are able to mutate interior, we are able to achieve interior mutability with RefCell. And as you can see, it's pretty easy. Now where you can use it is in such similar scenarios when you don't want to allow overall mutability, but you just want to have the interior mutability allowed, and just make sure to not allow memory leaks. As you can see, if node 3 was pointing to node 1 and node 1 was always pointing to node 3, we could easily run into memory leaks. Now, after we understand RC, cell, RefCell, and we understand how can we easily run into memory leaks, let's move to OnceCell. Again, pretty useful. So as the name suggests, OnceCell, meaning you can only achieve interior mutability once. If you try to do it twice, you will get an error. So let's see. Let's say we wrap it in OnceCell, and then what we do here is, instead of none, we'll just do OnceCell new. Similarly, OnceCell new. And let's say we try to set. So what we do is node 1 dot points dot set. As you can see, we have a set here, and we set to sum and RC clone. Again, the concept that we read that start remains the same. We want to achieve this using shared ownership. And then, because this could also raise the error while setting twice, so we'll just expect an error saying already set. And let's say we print all good, value set. So let's just print this. Now let's say what happens when we try to run this. So let's say we try to run this, and as you can see, it prints all set, all good, value set. Now let's say, what if we try to do it twice? So we copy this and we try to set it twice. So let's say here, instead of setting it to node 2, let's say we set it to sum none, or even we can set the same value as well, but here let's say for a change we set it to none. And let's remove this from here and paste it here. Actually, we wanted to remove, so let's remove it. So now we set once, we print all good, value set, and then we try to set again. So let's see what happens now. So let's go back to our terminal, we run. Okay, so as you can see, first it says sets, and then it basically says already set, and you get a error saying it's already set, and the main thread panicked. So straightforward. When do you use OnceCell? When you only wants to allow interior mutability once. So that's when you use OnceCell. Now let's move to our last for the day, which is our LazyCell. So let's try to understand LazyCell with a more simple example. So by the word LazyCell, we know that it should be something that is associated with the word lazy. That's exactly true. So here it helps us in lazily computing or initializing. So let's see with an example. After LazyCell, we'll get a summary of all of these cells and when to use it, and what are some use cases that you should eye for using these. So let's say we have a lazy value, and we have LazyCell new, and here we can pass the closure. So let's say we print saying initializing value, and then let's say it's initialized to 400. After which we can add a print here saying print before accessing lazy value. So right now we are not yet accessing the value, and then let's say we try to access it. So print, and here we can say access first time, and let's say lazy value. Then we print again and we access second time and lazy value. Pretty straightforward. Let's run this and try to understand. Okay, so as you guys can see, before accessing the value, which is right here, till this point, the initialization is not yet. When we access for the first time, that's when like initializing value. So initializing value, and after that it prints accessing for the first time. And then when we access for the second time, it doesn't reinitialize. So basically initializing only occurs once. So that's where LazyCell helps you, because as I mentioned, it's associated with the word lazy. Now let's get a summary of all of these, when to use it and in which environment can we use them. So let me try to explain with a summary of when can we use each of these. So RC is not thread safe, and when to use single thread reference counting. For that we can use it. And example use case is sharing read-only data in a tree-like data structure. So as we saw with the nodes example, so we can use RC there for reference counting. So we can, share the ownership as well. And then we have RefCell, again, not thread safe. And for mutability at runtime in a single threaded code, and provides interior mutability for graph where data needs to be modified. Similarly, cell, again, not thread safe, like small copy types like integers with interior mutability, as I mentioned, must implement copy thread. Only then you can perform mutability using cell. And storing and updating simple counter. And then we have OnceCell, which is only that is thread safe, and for single initialization, like you want to only initialize once, for example db initialization, loading a config file, or caching, you want to only initialize once and then use it. And then LazyCell, thread safe, no. Lazy on demand initialization, so it's like on demand, as we saw in the example. When we try to access it, that's only when it tries to initialize. And deferring the creation of expensive objects. So if we have some expensive objects and then we want to only initialize them if they are required, they are accessed, so that's when we use these LazyCell. So that's kind of a basic overview or summary which we saw for all of these. So that's it for this video, guys. I hope you guys learned something new. If you do, like the video, share with your friends. As always, I'll catch you guys in another video with something more interesting. I'll catch you.